Good evening everybody. Welcome to the class of Industrial Inorganic Chemistry once again, where we are talking about how we can get the sulfur as well as the different sulfur compounds. And definitely we will talk about at first the production of huge amount of sulfuric acid, what is industrially very much required for all the different purposes. So, in terms of the production of sulfur, what we know now that the earth crust or below the earth crust, we have a huge deposit of sulfur in many places. So, sulfur we can get it from its pure elemental form as S8, and we can process it for its purification or its regular utilization. Next, we now see that how we can get from hydrogen sulfide, that means our H2S, as well as sulfur dioxide. So, these are the two very industrially pollutant gases what we produce as a side product in some different reactions or manipulation of some reactions where we are handling sulfides as well as other sulfur compounds. So, if we can have a huge source of hydrogen sulfide, that means H2S, as well as sulfur dioxide, how we can get the elemental sulfur out of this. So, one of the good source of H2S is our natural gas, as we all now know that the CNG and the crude oil or the coal. So, during the production of the natural gases or the compressed natural gases, that means the CNG, or during the production of the crude oil, some amount of sulfur as well as the sulfur based compounds are eliminated as H2S. So, how we can get elemental sulfur, that means S or H2 or S8 from your hydrogen sulfide gas, that means H2S. So, the best technique is simply the oxidation process, that means sulfur is present in H2S as H2 minus, that means the sulfide ions or the sulfide anions, which is doubly negative. So, doubly negatively charged. So, this H2 minus has to be oxidized to H0. So, one such procedure is the typical process is Claus process. So, the Claus process is the industrially known process where we basically utilize the oxidation of hydrogen sulfide H2S by O2, the oxygen from the air or any other source in pure form. So, what happens basically from the chemical reaction point of view or the stoichiometric reaction of H2S with O2, we see from the first reaction where two molecules of H2S is reacting with one molecule of O2, giving us H2 plus 2 molecules of water. So, it is possible to oxidize your sulfide ion by O2, giving us the elemental sulfur as H2 form for your chemical balance or balancing the chemical equation. We write it in the form of H2, but in all these cases it is basically forming as the S8. So, S8 species will get here as well as the O2, which will be reduced back, that means O2 is in the zero oxidation state, will be reduced back to your water molecules. So, we get that in a nicer way, that simple oxidation by O2 of the H2S, we produce S2, which is your elemental sulfur. So, if our environment, the atmosphere is also contaminated with H2, and if we are able to detect the source of that H2S, that means some industry is eliminating H2S to the environment, what we can do? You can do some simple thing, that whether we will be able to pass that particular H2S in some reaction chamber where it will be oxidized by simply air or the O2 present in air. So, simple oxidation chamber through which your H2S can pass. So, that oxidation chamber will convert your entire H2S to elemental sulfur. So, there is no need to worry about the H2S what we are producing industrially, such that we are eliminating and we are discharging it into the air. So, we are not discharging it if we can take proper precaution for managing that particular H2S. And the second process is basically directly related to the two things, that what we are writing at the title, that sulfur from both, that means sulfur from hydrogen sulfide as well as sulfur dioxide. So, there also, instead of using O2, we can use SO2 as your oxidizing agent. So, this SO2 now can disproportionate, the reaction is that, or the reverse of the disproportionate reaction, what we can say is the conproportionation reaction, that means S2 minus is with reacting with S in the tetravalent state, that means SO2, the sulfur oxidation state is +4. So, the conproportionation reaction between H2S and SO2 will give us S8 and once again your water molecule. So, we can have two things, either you can have a good supply of O2 in your hand to take out your H2S or sulfur dioxide in your hand, such that you can destroy the amount of H2S what we are eliminating or removing or discharging into the atmosphere. So, as a result what we are getting something that we can produce sulfur, the elemental sulfur production from H2S or SO2, and the process is basically the process is not PROCESS. So, the process basically requires a combustion chamber where you can burn the thing, that means it will have a high temperature reaction, a waste heat boiler, that means some amount of heat is being wasted. So, we will have some waste heat boiler attached to it and the reaction is catalytic one. So, two catalyst filled reactors. So, we will have the reactors even for your reactions between the two components. In case of H2SO2, both of them are gases. In case of H2S and SO2, both of them once again they are also gases. So, this will be filled with two catalyst filled reactors. So, the catalysts are available and those catalyst filled reactors will be utilized for these simple reactions. So, the produced elemental sulfur, what we are producing in a huge amount, or we are isolating those from the natural sources, from the earth crust or some volcanic eruption. Out of that amount of sulfur what we are producing, basically we can consider it as a industrial thing, that one particular industry is basically devoted for the production of sulfur or the consumption of sulfur, because our main goal of knowing all these things, the discussion is focusing on the conversion of those sulfur, that means the elemental sulfur, to some useful sulfur based compounds. So, about 85 to 90% of the sulfur what we are producing is basically meant for the production of sulfuric acid, because this is the main thing, because this particular one, like that of our nitric acid, this sulfuric acid has a huge demand in the industry and large amount of sulfuric acid we have to produce for different purposes. So, sulfur is given to you, the elemental sulfur is given to you. You should know how we can convert it to sulfuric acid and what should be the corresponding industrial process, that means the industrial procedure, that will tell us the underlying principle behind the inorganic chemistry dealing in industry. Because this particular one, that means this elemental sulfur, main amount, that means up to 90% is consumed for sulfuric acid production. It is also utilized for the production of some other things, that means when we require sulfur dioxide also. Just now we have seen that how sulfur dioxide can be consumed for the production of sulfur. Now, the reverse reaction, if we require sulfur dioxide and we have only the stock of elemental sulfur, we should know that how it can be converted to sulfur dioxide for ready use of that sulfur dioxide. Then one most important liquid, basically this is liquid carbon disulfide CS2 is a very useful one, and that carbon disulfide, if time permits, in afterwards we will see that it has lots of applications, starting from your laboratory detection of alcohols. As we all know that alcohols are ROH and that alcohol in presence of this particular compound, that means carbon disulfide CH2 in basic medium or alkaline medium in terms of ammonium hydroxide, sodium hydroxide or potassium hydroxide, that can be converted to, that means the alcohol can be converted to xanthates, and those xanthates are of the corresponding salts depending upon the base what you are using. If you use ammonia for your base, it will be ammonium salt of that xanthate. If we use ethyl alcohol for the conversion of that particular process, we will get potassium salt of ethyl xanthate. Similarly, if we have the sodium hydroxide or potassium hydroxide as bases, we will get their corresponding sodium salts or potassium salts as the corresponding xanthates, because this has very good application industrially also, that means for the production of the different types of cellulose materials, the cellulose acetates or the cellulose xanthates basically, for their final production and all these things. This particular reaction is taken place over there through the conversion of alcohol to xanthate. Then direct sulfur, that means we know that the sulfur is very much utilized for sulfur-sulfur Claus linking from our protein molecules to the rubber molecules. So, sulfur-sulfur Claus linking between a chain of a polymeric unit, whether it is a protein, that means the biomolecule, or it is a synthetically prepared protein that polymer chain, we can go for the vulcanization. So, elemental sulfur is utilized for vulcanization of those materials also. Then as we have seen that the CH2 and for the phosphorus pentasulfide production as well as thiosulfate production. So, this also we have seen earlier that how P4H10 can be formed or P4H10 can be produced from elemental phosphorus as well as elemental sulfur. So, earlier we have discussed all about how we produce phosphorus from mineral source or the ore source. So, elemental phosphorus was in our hand. So, we should have the corresponding supply of sulfur now, and at a high temperature reaction it basically converted to phosphorus pentasulfide, whose molecular formula is basically the dimer of that pentasulfide, which will be P4H10, and some amount of thiosulfates can also be dependent on the availability of elemental sulfur for its reaction, that we will also see that bisulfides or the sulfides SO3 only, SO3 2 minus, when it is directly reacting with sulfur. So, that sulfur attachment to the sulfide ion SO3 2 minus will give you H2O3 2 minus, which is your thiosulfate anion. So, it can also be utilized for different sulfur dyes, sulfur containing putty for their building material, gunpowder and fireworks, because the sulfur is the main constituent of the different fireworks. We know the sulfur is being burned as sulfur dioxide. Then sulfur bearing concrete material, slow release fertilizers are also there, because some amount of sulfur is utilized, and when sulfur is converted to sulfur dioxide, this particular fertilizer can be taken away as a slow release fertilizer, and definitely for the pharmaceuticals, because the incorporation of sulfur as different sulfur drugs or the sulfur present in the beta lactam ring. So, the sulfur present in the big organic molecule can also come from elemental sulfur. So, the sulfur is also utilized for making the different pharmaceuticals, and definitely what already we told you that is for rubber vulcanizing agent. So, these are the main uses of elemental sulfur what we can use, but the major utilization of elemental sulfur is the production of sulfuric acid. As I told you that 85 to 90% of it will be utilized for sulfur bearing oxides, and then conversion of that particular oxide to the highest possible oxide, that means sulfur dioxide to sulfur trioxide, and then to H2SO4. So, how we go for that? So, the direct reaction, direct chemical reaction if we see, which is SO2 plus half of the O2 will giving you SO3. So, towards the left basically what we are doing nothing but elemental sulfur is in your hand and you burn it in plenty of air, huge amount of air. So, sufficient air is available. So, air will be available for oxidation of your sulfur to sulfur dioxide, and that sulfur dioxide has to be converted to sulfur trioxide. So, this is a different step of your chemical reaction, and always try to remember that when we burn in excess air and whatever amount of other thing we add there, we will not get sulfur trioxide directly from elemental sulfur. It has to go through sulfur dioxide formation. So, that sulfur dioxide formation is basically giving us some idea that in a double step reaction, SO2 is being converted to SO3, and then through the absorption of your water molecule. That means, we can have some mechanism where water can be absorbed by the gas molecules which are SO3. So, when SO3 is being absorbed by water molecules, so direct incorporation of that particular one in SO3 producing H2SO4, and with the variation in different concentration. As we all know that hydrochloric acid which is available in water medium, but the HCl what we produce is basically a gas. So, the dissolution of that HCl, that means the hydrochloric acid gas if we consider. So, that HCl when it is absorbed in air, we basically get as your hydrochloric acid. But here the direct reaction of that H2O with SO3 is giving us H2SO4. So, water will be one of the constituent of that H2SO4. So, in a highest possible concentration of that H2SO4, we have the maximum amount of sulfur trioxide in it, and sometime we can see also, we know that this produced H2SO4 in the first step can further absorb some amount of SO3. So, H2SO4 plus SO3 can give us something which we all know that this is basically the oleum. When you have excess amount of sulfur trioxide present in the produced sulfuric acid, this is giving us a highly concentrated sulfuric acid version, which is basically some portion is the anhydride of sulfuric acid. So, stepwise what we can go from combustion getting sulfur dioxide, and the reaction is exothermic, that means it is producing some amount of heat and is carried out industrially in a combustion chamber and with spray burners for liquid sulfur. So, liquid sulfur basically, so the solid sulfur is not the powder we are spraying, but spraying the liquid sulfur. So, the molten sulfur and dry air is utilized for the oxidation of that sulfur to sulfur dioxide, and that liquid sulfur not at a very high temperature, but at a temperature of 140 to 150 degrees centigrade, because at that particular temperature it reaches a minimum viscosity value, is sprayed through jets, very fine orifice of that particular one. So, the supply line will have some small jets, and the jet is finally divided into droplets into the combustion chamber. So, the liquid sulfur is basically getting injected into the combustion chamber where it is being burned to form your corresponding sulfur dioxide. So, if we get the droplets, the contact of that particular liquid sulfur with oxygen, that means O2 will be the highest one. So, the conversion to SO2 is also should be the highest one, until and unless we talk in terms of the solid sulfur is burning in some medium in presence of oxygen at some temperature coming from some flame or some other thing. So, the plants we definitely require for that particular industrial production. So, the three plant types are known with pressurized atomizers, that means we are forcing the liquid sulfur to spray inside, then binary burners and rotary atomizers. So, atomizers are nothing but very fine droplets, the mists are forming from the liquid sulfur and which are being sprayed inside. The way we spray for the different atomizers, we know that the atomizers are required for different spectrometers such as your atomic absorption spectrometer. where the system is such a manner is formed that we basically spray and we get the atoms of the corresponding elements or the metal ions. So, we get the hot sulfur, and that hot sulfur at 150 degree centigrade is passed down into the inner wall of a beaker. Basically, if we consider that you have a beaker and which is rotating at a very high speed from 4000 to 6000 rpm, and it is forming a film of sulfur. And now that particular beaker is surrounded by a ring slit into which high velocity air is introduced. So, we are bringing that particular sulfur as a film into the contact of the air, such that we get the reaction directly from sulfur with oxygen, giving you sulfur dioxide. So, the sulfur film what is forming over there through that rotation is atomized by the air stream entering the chamber and the centrifugal force and the burnt out and then burnt. That means, it is then quickly burnt out, and the burnt out process is basically giving us the corresponding sulfur dioxide. And we have that SO2 now in our hand, and we will see next that how we can convert that SO2 to SO3 before getting that sulfuric acid, that means H2SO4. So, one other source, not the direct elemental sulfur. So, any sulfide source, it is also a good source of sulfide ions, as we have seen earlier, that if we use H2S, we can produce elemental sulfur. Similarly, the corresponding sulfidic ores like FeS2, the pyrite ore. So, FeS2 having polysulfides is not a pure S2 minus, but is a basically a polysulfide type of thing. That means, S2 has a overall charge of 2 minus. So, that polysulfide type of thing can also be oxidized in presence of air, but at a very high temperature of say 800 degree centigrade, and that temperature is utilized for the production of sulfur dioxide. So, sulfur dioxide is formed. So, whatever amount of sulfide was present which is attached to that particular ore is taken away as sulfur dioxide, leaving behind you that iron oxide, that means the ferric oxide. So, this particular oxidation process is carried out in a multiple hearth roaster. Roasting, we all know, that is basically a burning process. That ore roasting is a very common procedure for making all these things, and sometimes we basically get for the corresponding value addition of all these things. So, if your iron pyrite is not a very useful ore or mineral for the production of iron or steel making industry, what we can do? We can go for its conversion from FeS2 to Fe2S3, because we know as the hematite or magnetite, these oxides like Fe2O3 or Fe3O4, they are very useful ores for iron and for steel manufacturing. But at the same time, we are also producing sulfur dioxide, but now we are focusing our attention on the other part, that means the production of SO2 from these ores, and that SO2 will be utilized for sulfuric acid production. So, a particular industry which is focusing their attention for making iron and steel industry can have some byproduct of sulfur dioxide, and if they are careful enough without dumping that SO2 in the air or atmosphere, they can utilize that particular SO2 formation from that reaction for the production of sulfuric acid. So, not only that industry will be devoted for making iron or steel or any other material based on iron, can also be able to produce sulfuric acid from a very straight cut reaction of getting sulfur dioxide, converting it to sulfur trioxide, and that sulfur dioxide through water absorption giving you H2SO4. So, these basically can be carried out in multiple hearth roasters, rotary tube furnaces, and sometimes the fluidized bed furnaces. This is a typical terminology for these, that you have the fluids and you have the beds where that contact of the corresponding reactions can be achieved, and these are basically the furnaces, that means a typical high temperature reaction. So, for this particular example, that in fluidized bed furnaces, what happens basically there, There a cylindrical roasting shaft is available that extends upward conically to a settling chamber. So, these are basically, because these are the basic components what we are talking in terms of only the components of these. If we try to avoid a detailed drawing the flow chart of all these things, but we should know the basic component, because we are focusing our every attention for the product formation and how we are achieving all these through the reactions and what are the reaction chambers basically. Because when you do some reactions or this sort of reactions in the laboratory, we all know that the round bottom flask, the beaker and all these small containers are available for your reaction, but when you go to industry, you have all these huge furnaces or the chambers available for its conversion. So, you have a settling chamber and the sulfidic material, that means the ore material, that FeS2 material which can be dumped over there and which can be burnt in air for roasting, and roasting is done at a very high temperature. It is less than 800 or more than 800, from 650 to 900 degrees centigrade, and the air basically is allowed to pass through a grill. So, that means we are spreading the air such that you can have a huge or good contact over there, and you have uniform distribution in the shaft, and a fluidized layer is produced mainly consisting of iron 3 oxide. So, during that oxidation process, the all particles of FeS2 will be oxidized and we get that thing. That means, we are only interested to get that particular material as your gas material. So, if your solid material remains intact and is only converting from FeS2 to FeO3, we are happy to have the corresponding oxygen for burning process as your sulfur dioxide. So, air or O2 is entering into the chamber and SO2 is going out from that particular chamber, converting your FeS2 to Fe2S3. So, the hot gases is basically a mixture containing up to 14% of sulfur dioxide and a very little of sulfur trioxide, because some amount of sulfur dioxide can also form, and is cooled in a waste heat boiler. So, because the temperature is very high, it is 650 to 900 degrees centigrade. So, the gas what we are producing is also at a very high temperature, and when we cool it at a low temperature is basically we get some waste heat boiler. That means, heat is being removed from the medium. So, waste heat boiler is there, that means some cooling tower is available, and that particular tower is meant for cooling the SO2 produced from that particular reaction, and that particular production is basically giving us some elevated temperature of the air, if air is used for your cooling that particular boiler, or water if water is used for cooling process. So, like FeS2, we can have some other sulfidic ore which is also your zinc sulfide ZnS, which is known as zinc blende, which can also be utilized for this particular purpose using the fluidized bed technology. So, depending upon the availability of the ore, whether we get FeS2 as a good supply or regular supply or availability in the near vicinity of that particular industry, we can go for FeS2 for use, otherwise we can go for zinc sulfide for its production of SO2. So, this basically we have in our hand, that means we get it as your corresponding formation of SO2, and the roasting gases, that means if we use O2 and that O2 is giving you SO2, and that SO2 is basically the roasting gas, that means the high temperature gas what we are having, and 14% of this is SO2, the remaining is your O2. So, it will be purified by dust removal in a cyclone or electrostatic filter. So, electrostatic filter will be there where the particles, that means the dust particles will be removed or will be settled down at the bottom of the filter, or a scrubbing with jet scrubbers after cooling. So, once you cooled it, you can pass through a scrubber So, basically scrubber having very small pores basically, and through those pores the gas is being passed and the particles will be retained by those scrubbers, and the jet scrubbers is being used for that particular removal of those particles. So, we have now reached to the position where we can talk in terms of the conversion of SO2 to SO3 and how we can convert it now. So, we now write the chemical reaction as SO2 plus 0.5 or half of O2 giving you SO3, and the heat of the reaction, the delta H, is also little bit you should remember, because we are talking basically in terms of the temperature and the temperature what is being utilized for that particular conversion. But the delta H values are sometimes a very good guidance whether we get that particular conversion for a different types of catalyst, that means the development of the catalyst. Some people are also working on the development of the catalyst for this model reaction. We can consider this as a very simple model reaction, that means how easily we can convert SO2 to SO3 by using a new type of catalyst. So, all these cases or all these processes we are utilizing some amount of some model reaction. So, this can also function as a model reaction for its suitability of that particular catalyst, how good that catalyst is for this simple reaction. So, when we go for a low temperature conversion, so a low temperature should be used to shift the chemical equilibrium towards the right. That means the cooling process should be utilized for now this oxidation, that means SO2 to SO3 oxidation, and to shift the equilibrium towards the right, hence increasing the percentage of field. So, whether your reaction is exothermic and endothermic, that basically guiding us that whether you can change the yield of the reaction, because always we should be able to maximize the yield of a particular reaction. So, we will just continue in our next class what we are happening over here, what basically is happening for this particular conversion, and we will see what sort of catalyst, most used catalyst is utilized for its conversion. Thank you very much.